Hello and welcome to another one of our online lecture videos for differential equations. Today we're going to be talking about linear and almost linear systems. We'll probably save most of the discussion for almost linear systems for the next section. So we have some theorems to take a look at. First, a critical point is called isolated if some neighborhood of that point contains no other critical point. So critical point is isolated if some neighborhood of that critical point contains no other critical point. And then we have a theorem for stability of linear systems. We say let lambda sub 1 and lambda sub 2 be the eigenvalues of the coefficient matrix A of the two-dimensional linear system. We have dx dt is ax plus by, dy dt equals cx plus dy, with ad minus bc not equal to 0. Then the critical point at 0, 0 is, we say asymptotically stable if the real parts of lambda sub 1 and lambda sub 2 are both negative, stable but not asymptotically stable if the real parts of lambda sub 1 and lambda sub 2 are both 0, so that lambda sub 1 and lambda sub 2 are just imaginary plus or minus qi, and unstable if either lambda sub 1 and lambda sub 2 has a positive real part. Now, important here to notice that we're talking about a coefficient matrix, and that's going to come into play at some point during our lecture here today. We have a theorem here on the stability of almost linear systems. Let lambda sub 1 and lambda sub 2 be the eigenvalues of the coefficient matrix of the linear system. dx dt is a star times x plus b star times y, and dy dt is equal to c star x plus d star y, associated with the almost linear system in dx dt is ax plus by plus some function r of x comma y, and dy dt is equal to cx plus dy plus some function s, a function of x and y. Then if lambda sub 1 is equal to lambda sub 2, and these are equal real eigenvalues, the critical point 0, 0 is either a node or a spiral point and is asymptotically stable if lambda sub 1 and lambda sub 2 are negative and unstable if positive. We would say if lambda sub 1 and lambda sub 2 are pure imaginary, then 0, 0 is either a center or a spiral point, and may be asymptotically stable, stable, or unstable. And otherwise, that is, unless lambda sub 1 and lambda sub 2 are either real, equal, or pure imaginary, the critical point 0, 0 of the almost linear system is of the same type and stability as the critical point 0, 0 of the associated linear system that we gave earlier. And let's go ahead and take a look at some examples, but first I'd like to show a table that I think breaks this down very nicely. So when we go to find the eigenvalues, and we refer to them as lambda sub 1 and lambda sub 2, here the chart uses r sub 1 and r sub 2, so not to try to confuse, but just pointing out a distinction there. If we have eigenvalues that are greater than 0 and distinct, we have an unstable node. If they're negative, both of them negative and distinct, we have an asymptotically stable node. If we have one eigenvalue is positive and the other is negative, we have an unstable saddle point. If they're equal and they happen to both be greater than 0, then we have an unstable node, either proper or improper. If they're equal and they're both negative, then we have an asymptotically stable node, either proper or improper. If we have that they're complex, then we have a spiral point, and depending on the real part, whether it's positive or negative, we'll be able to tell the stability. If the real part is positive, we're unstable. If the real part is negative, we have asymptotically stable spiral point. And then if they are pure imaginary, if it's just the complex part with the real part 0, then we say we have a stable center in that case. And we'll go ahead, we'll talk about how we can get this information very quickly from the eigenvalues, and then we'll also try to connect it back to some things that we said earlier in the course. So first, we would like to determine the nature and type of the critical point at 0, 0, and tell whether it's asymptotically stable, stable, or unstable. Then we're going to verify our conclusion using some type of phase portrait to take a look at. And let's go ahead and start with this example. Now, we're not going to verify that 0, 0 is a critical point, but we can certainly see right now that if we go ahead and pick 0 for x and 0 for y, then dx dt and dy dt are both going to be 0. So it is, in fact, a critical point. We can just sort of verify that by inspection. And if I want to rewrite this using my favorite notation, that shorthand notation, I would say x prime is equal to negative 2x plus y, and y prime is equal to x minus 2y. And just like we did earlier in the course, I can build from this a coefficient matrix, call that matrix A. So sorry about that. And our coefficient matrix A, we just take the coefficients in order. So x prime, the coefficients on x and y in that order, is going to build my first row. So negative 2x, so write negative 2, plus 1y, so write the 1. And then y prime, the right-hand side, the coefficients on x and then y in that order are going to build my second row. So we have 1x minus 2y. And remember what we would do from here. We would want to take a look at a minus lambda I. And here I refers to that 2 by 2 identity matrix. And we've seen this before, so we know the effect of this is that anything off the main diagonal is going to stay preserved. And for those entries that are on the main diagonal, from upper left to bottom right, we subtract lambda. So negative 2 minus lambda, and then another negative 2 minus lambda. Now remember, from here we want to find the determinant of this matrix. So determinant of a minus lambda I. That's going to give us, we multiply on the main diagonal, so negative 2 minus lambda times negative 2 minus lambda, and then we subtract the product on the off diagonal, so then minus 1 times 1, and we set that determinant equal to 0. Right, force that determinant equal to 0. And if we expand this out, so here I want to FOIL, negative lambda times negative lambda gives me a positive lambda squared. We get a positive 2 lambda and then another positive 2 lambda. Negative 2 times negative 2 gives me 4. I don't want to forget about this. Clean that up just a bit. So negative 2 times negative 2 gave us 4. And then we have this minus 1 times 1, so minus 1 equals 0. We got that 0 up there. I can go ahead and combine these like terms, right? The 4 minus 1, go ahead and combine them. And the 2 lambda plus 2 lambda I can combine as well. So we get lambda squared plus 4 lambda plus 3 equals 0. And then I'd like to factor this if I can. So we'll say, well, here, let's try to factor. So lambda in the front. And then two numbers that multiply to positive 3 and add to positive 4. Well, we'll say, okay, lambda plus 1, lambda plus 3. And what is this going to give me? Well, when I solve for lambda, it gives me lambda sub 1 equals negative 1, and lambda sub 2 equals negative 3. Now, what's nice about this linear system is as soon as I find the eigenvalues, I can actually tell what's happening at that critical point right away. So we could actually make a comment here. We could say, since lambda sub 1 and lambda sub 2 are both negative, well, we could say a little bit better here, both negative integers. This means the critical point at 0, 0 is an asymptotically stable node. So since we have our eigenvalues are both negative integers, they're distinct negative integers, the critical point at 0, 0 is asymptotically stable node. And so a good question is, well, how do you know that? How do you know that without looking at that table from previously? Try to keep in mind the role that these eigenvalues play in building our solution to our first order linear system. And we took a look at examples like this earlier on in the semester. So remember what this means. This means both x a function of t and y a function of t are of the general form c sub 1 e to the minus t plus c sub 2 e to the minus 3t. Right? Remember that those eigenvalues become coefficients in the exponent of some exponential function, right? With e as the base. So if we look at this, we'd say, okay, like we said earlier, as t increases, as t goes to infinity, this is going to drive both of these general forms for x and for y to 0. So we would say since x and y both are of this general form, that means as t goes to infinity, that means x goes to 0 and y goes to 0. But what's really great about this is if we're thinking about this in terms of how the solution looks, building off of what we did previously in the course, we get this information now very quickly. Looking at these eigenvalues, I can say right away, they're both negative, they're distinct, so I know how this is going to look. They're both negative integers, so right away I can tell, oh, okay, so this is going to give me something that's an asymptotically stable node. Right? And we can be thinking about how that generic form looks, you know, or write it down sort of on the margin somewhere, but truthfully, we don't even really need to express it that far. The idea of the section is to really use these eigenvalues to make the judgments that we're making. But I like to keep in mind this information from behind the scenes, what's really sort of happening then with our first order systems. Let's see if we can verify this now through a phase portrait. So we said 0, 0 is an asymptotically stable node. Let's see what we get here. So here I have just a stream plot, 0, 0, right at the center. We see that we're stable. All of our trajectories are moving towards that critical point. So we're able to verify what we said visually with some idea of a phase portrait. Let's take a look at another example. And again, the critical point is at 0, 0. We can verify that, of course, quick to sort of tell by inspection that 0, 0 is a critical point. But if I go ahead and rewrite this system with my favorite notation, x prime is equal to x plus 2y, and then we have y prime is equal to 2x plus y, I can build from this my coefficient matrix A. And we'd say, okay, so here using x prime to build that top row, we have 1x and then 2y, so 1 and then 2. Y prime to build the second row, we have 2x, so write the 2, plus 1y, so write the 1. And now it's just a matter of getting those eigenvalues. So we'd say A minus lambda I, where I is the 2 by 2 identity matrix. So on the main diagonal, we have 1 minus lambda and 1 minus lambda. On the off diagonal, we keep those entries, we preserve them, 2 and 2. And we want to find the determinant. So the determinant of A minus lambda I, and that's going to give me 1 minus lambda times 1 minus lambda minus multiplying on the off diagonal, so minus 2 times 2. And we set this equal to 0. And so we'll go ahead and expand this out. Negative lambda times negative lambda gives me a positive lambda squared. Negative lambda times 1 gives me minus lambda. 1 times negative lambda gives me another minus lambda. 1 times 1 gives me plus 1. And then minus 2 times 2 is 4. And we want to set this equal to 0. And now we can combine our like terms. So we'd say, okay, here we have lambda squared minus 2 lambda. And then 1 minus 4 gives me negative 3 equals 0. And I want to know from here, can I factor this? Well, sure. Lambda in the beginning, numbers that multiply to negative 3 and add to negative 2, well, we would say minus 3 and plus 1. So from this, we get our eigenvalues. Lambda sub 1 equals 3. Lambda sub 2 equals negative 1. Now, just from looking at these eigenvalues, we should be able to classify the behavior. So let's go ahead and sort of talk a bit about that. What do you notice about these? They're integers, of course. One of them is negative, the other is positive, so they're different signs. And that's going to be very telling here. So we can say since lambda sub 1 and lambda sub 2 are different signs, well, we can say are integers with different signs, one positive, one negative. This means the critical point 0, 0 is, what do you think it is? What do you cast your vote now? Is an unstable saddle point. Unstable saddle point. And I can tell that since I have these integers for my eigenvalues, but one is positive and one is negative. And it's really the positive one that's ruining it. But if we try to connect this back to what we said earlier, we could say both x at t and y at t are of this general form where we would have c sub 1 e to the 3t plus c sub 2 e to the minus t. And certainly as t goes to infinity, this sort of e to the minus t part is going to, vanish. It's going to go to 0. But this e to the 3t part, it's going to stick around, right? And that's going to get to sort of call the shots. That's going to sort of dictate the behavior eventually, right? So we'd say, okay, well, since not both of the pieces are decaying, that means we're going to end up diverging headed to infinity. So I'd be able to say then, as t goes to infinity, we're going to have that x goes to plus or minus infinity, and y goes to plus or minus infinity, depending on how those coefficients end up looking, right? But what's interesting is since we have this one part that is sort of disagreeing with the other, remember with those saddle points, we see this interesting behavior where it almost looks like we're headed towards the critical point at first, only to maybe sort of seemingly at the last moment dart away from it. But so this is definitely going to be a saddle point, right? I have a positive and a negative eigenvalue, which is going to build that disagreement in behavior between my exponential functions. So that's what we're going with here, right? Lock in those votes. We have an unstable saddle point at 0, 0. What does the phase portrait say? There we see it right in the center. 0, 0 is my critical point. And I have this interesting behavior where my trajectories, although some of them look like they're headed, at the very last second they go, whoops, see, faked you out. You can't stop, won't stop. You don't know what I'm going to be doing. I'm all sorts of crazy, right? So these trajectories, they look like maybe they're doing something, then they try to do that sneak move, right? Woo, what am I doing? What's my dance move, right? So we got that saddle point. God, I always get a good time out of those saddle points. They're always fun to sort of take a look at. They're so crazy. All right, let's take a look at another one. I hope you're enjoying this as much as I am. I'm having a really good time today. We got that critical point at 0, 0. We can tell that by inspection. So let's go and rewrite our system the way we like. X prime is 3x minus 2y. And y prime is 4x minus y. And build that coefficient matrix A. So you'd say, well, here, x prime for the top row, that's a 3 from the 3x, a minus 2 from the minus 2y. Y prime builds that second row, so 4 from the 4x, minus 1 from the minus y. And if these were out of order, I'd want to make sure to reorder them. It should be x and then y in that order. So make sure you're careful with anything small like that we're, always alert. You got enough coffee to see those small things. And a minus lambda I, subtracting lambda on the main diagonal, Right? We've seen this stuff before in the course, and now we're just using it to get an idea as to the behavior at our critical point. And here we want to find the determinant of a minus lambda I. So multiplying on the main diagonal, we have 3 minus lambda in parentheses times -1 minus lambda. Then we want to subtract the product on the off diagonal, so that's -2 times 4, and set that equal to 0. We're forcing that determinant equal to 0. And if I expand this out, let's see, negative lambda times negative lambda gives me a positive lambda squared. Here we get negative lambda times -1 is plus lambda. 3 times negative lambda gives me -3 lambda. And 3 times -1 gives me -3. And then here I have minus and negative, so that's going to switch to plus. 2 times 4 gives me 8, is equal to 0. And if I combine my like terms, well, then here I get lambda squared. Lambda minus 3 lambda is -2 lambda. And -3 plus 8 gives me +5 equals 0. This does not look like it's going to factor, so there is no reason why we wouldn't go ahead and take a look at the quadratic formula. So we'd say lambda is equal to, I want -b, so that's -2, which is 2, plus or minus the square root of -2 squared. Now if I square -2 gives me 4, minus 4 times a times c, so that's 4 times 1 times 5, all over 2 times a, so all over 2 times 1. That's going to give me lambda equals 2 plus or minus square root of 4 minus 20 all over 2, or that's 2 plus or minus the square root of -16 all over 2. And thinking about that product property of the radical, we'd say, okay, lambda is equal to 2 plus or minus square root of 16 gives me 4. Square root of -1 gives me I, so we get 4i all over 2, which now I can go ahead and reduce. 2 over 2 gives me 1, plus or minus 4i divided by 2 gives me 2i. So we get this complex conjugate pair. The real part is there as well. We get 1 plus or minus 2i. So let's go ahead and talk about this, but what are you sort of thinking right away at first glance? So I'd say since our, what are you doing? Since our eigenvalues are lambda equals 1 plus or minus 2i, we have a spiral point at critical point 0, 0. However, we can say more than this, since the real part is positive, we have, I can do a better H, we have an unstable spiral point at 0, 0. Or thinking about that unstable spiral point, might not be bad to use that term source, unstable spiral source at 0, 0. So feel free, if you're comfortable, to drop those sort of key terms in there along the way. A good question might be, well, okay, so how do you know that? And remember, we're trying to reference back to how these general solution forms look. The general form for the solutions on both x and y is going to be e to the 1 times t, which is e to the t, times c sub 1 cosine 2t plus c sub 2 sine 2t. So thinking all the way back to the characteristic equation in some sense, we're saying the general form for both x and y I'm trying to do a bit of shorthand here, but just so that we're clear, these are the general form for the solution for both x at t and y at t. It's going to be this exponential function times our sinusoidal functions. That's where we get that spiraling effect from, because cosine and sine are just going to be oscillating as they usually do, but then the exponential function is what's going to create that really nice spiral aesthetic that we like. However, since the real part is positive, that means we get e to some positive number times t. So what I want you to notice is that as t goes to infinity, that x and y are both going to head to infinity. They're both going to diverge, right? So we get this spiral that's going to happen. So let's go ahead and see if we're saying we have an unstable spiral point at 0, 0. We can tell that information immediately from the eigenvalue that we get. Let's go ahead and see if we're right. Ooh, I always love how that looks. So 0, 0 right in the center, that's our critical point. And what are our trajectories doing? They're spiraling away from that critical point. And we get this really cool looking design. You know, this, you could almost even use this as like a personal logo, you know, for your own personal branding, for your social media. Say, what is that? Oh, it says, we got a spiral source, is what that is. But it's really cool, very iconic. Love it. Let's talk very briefly about the Jacobian, and then we'll move on to some linear systems and talking about linear systems that have critical points other than at 0, 0. The Jacobian is going to be a big candidate here to work with. It's something we can work with in these examples that I have for the rest of the lecture, but there's another way that we can actually view them as well. The Jacobian is really going to be important when we're working with examples in the next section, and that's something that we're really going to need the Jacobian for when we take a look at these almost linear systems. The Jacobian matrix is a matrix made up of partial derivatives of terms, defined as, we call it J for Jacobian, and here the Jacobian is evaluated at x sub 0, y sub 0. Now, what we're doing is we're building a top row for the matrix with the partial derivative f sub x and f sub y. So we take so let's just sort of recap here. We're saying that if x prime is equal to some function f, a function of x and y prime is some function g, a function of x and y, and we'll say with critical point at x sub 0, y sub 0, then what we do is we build this Jacobian matrix. We take the partial derivative of f with respect to x, and then the partial derivative of f with respect to y in that order builds the top row. For the second row, and this builds a 2 by 2 square matrix, we do g sub x, so that's the partial derivative of g with respect to x, and then g sub y, which is the partial derivative of g with respect to y. After we do that, we then want to evaluate those partial derivatives. So for any of those partial derivatives, we evaluate them at the critical point, meaning whatever the x value is, whatever the y value is from our critical point, we plug those into the partial derivatives in this arrangement into a matrix, and that just gives us a constant matrix. We're going to have numbers in each of these positions for our entries. We then work with that as our coefficient matrix. So that's really sort of the idea. But let's talk about how that can be applied to these linear systems that we have here and what that sort of means. So assume the following system has a critical point at x sub 0, y sub 0, classify the critical point's type and stability, verify this conclusion using a phase portrait. Some computer utility, Python would be ideal for that, right? So what I can do right away is I can find the critical point. Since it's not at 0, 0, here we have x prime equals 2x minus y minus 2, and y prime equals 3x minus 2y minus 2. I want to set x prime and y prime equal to 0. So 0 equals 2x minus y minus 2, and 0 equals 3x minus 2y minus 2. So just taking my derivatives, setting them equal to 0 to try to find the critical point. Now what's nice is this very first equation, I can solve it for y pretty quickly. If I just add y to both sides, I get y equals 2x minus 2. And I can use this as a substitution into the second equation. So then we get 0 equals 3x minus 2 times y. But I can replace y with its substitution, which is 2x minus 2. And then we have minus 2. Now this gives me a linear equation on x, so I should be able to solve for x just like we would have done in pre-calculus. So 0 is equal to 3x, minus 2 times 2x is minus 4x, negative 2 times minus 2 is plus 4, minus 2. So here we get 0 equals minus x plus 2, and if I add x over, well, this means x is equal to 2. Since I have x, now I can find y just by plugging into the substitution statement. So y is equal to 2 times x minus 2, but I know that x is 2. So here we get y is equal to 4 minus 2, or just that y is equal to 2. So now we know where the critical point is. So the critical point is x is 2, y is 2. So it's not 0, 0, but it's 2, 2 is our critical point. Now from here, what we're going to do, or what we could essentially say in order to kind of shortcut this, is that when I go to build my matrix, I still just want a coefficient matrix. So it doesn't really matter that what this gives me is some linear system that isn't necessarily homogeneous. That is, if I set these equal to 0 and, if I work with these constants here, what I'm really trying to say is they don't really matter. They don't make a huge difference here, so long as they're just constants. If there were variable terms, if it was something with like an x squared or a y squared or a mixed variable term like x and y, or like a 2xy or a 3xy, that would be a huge issue. That would be something difficult to work with. But since these trailing terms that don't have any variable in them are just constants, they're fine to work with, and essentially we end up just ignoring them. And I'll explain why in a couple of ways. But first, let me build that coefficient matrix, just so we have it written down. So if I want to build the coefficient matrix, we call it that for a reason. It's just a coefficient matrix, meaning I still just take those coefficients. So if I'm looking, I have 2x minus 1y, and we kind of ignore that negative 2. So we just write down for that top row 2, negative 1. Same idea for y prime. It seems kind of a shame, but we just ignore this trailing constant. We write the 3 from the 3x and the negative 2 from the negative 2y. And this is what we're going to work with. Now let me justify this using the Jacobian first. And there's another way to justify it that I want to look at as well that I think is almost preferred to me. For something that's this minor of an offense, I think the Jacobian is kind of heavy artillery for something like this. F, my function f, which would be what x prime is equal to, is this 2x minus y minus 2. And g, let me do g in a different color, is what y prime is equal to, where g is this 3x minus 2y minus 2. Now if I take partial derivatives, these are already going to be constant. So if I go to what I said f was, if I find the partial derivative of f with respect to x, well, treating y as a constant, that just gives me 2. And f's derivative partially with respect to y, now treating x as a constant, just leaves me with negative 1 from that negative 1y. Similarly, if I take partial derivatives of g, the derivative of g with respect to x partially, treating y as a constant, just leaves me with 3. And the partial derivative of g with respect to y, now treating x as a constant, just leaves me with negative 2. And this builds from the Jacobian matrix. There's no extra step here because there's nothing to plug in, or nowhere to plug it into, rather, I should say. Just builds that coefficient matrix. So we could say the following. If we have something that's linear but just has an extra constant thrown in there at the end, it's just the coefficient matrix all over again is all we really have to focus on. So very little changes. So we would have that top row 2, -1, and then 3, -2, which is exactly what we were already working with down here. Now from here, the steps are really the same. So I build A minus lambda I. So subtracting lambda on the main diagonal, leaving those other entries alone, rewriting them, and then building that determinant of A minus lambda I. So 2 minus lambda times -2 minus lambda minus -1 times 3, setting that determinant equal to 0. We can work with this. So let's go ahead and expand this out. Negative lambda times negative lambda gives me positive lambda squared. Negative lambda times -2 gives me a positive 2 lambda. Negative lambda times 2 gives me -2 lambda. 2 times -2 gives me -4. And here I have minus and negative gives me plus. And then 1 times 3 gives me 3. And then equals 0. And let's combine our like terms here. So we'd say, here we get lambda squared. 2 lambda minus 2 lambda cancels, so that's gone. And then -4 plus 3 is going to give me -1 equals 0. And this will factor difference of perfect squares. So here we get lambda plus 1, lambda minus 1 equals 0. Gives me eigenvalues lambda equals -1, lambda sub 1 we can call that, and lambda sub 2 equals positive 1. Now keep in mind the critical point was not at 0, 0. That critical point was at 2, 2. We went and found that first. But just based on these eigenvalues, we should be able to tell the nature of that critical point. So the nature of critical point 2, 2 is, what do you think it is? Pause the video, yell it at your screen, then resume the video. Ah, I can hear you yelling. I'm just kidding. Did you yell? I don't know. Let me know on our discussion board if you're yelling at the screen when I recommend it. So we'd say here the critical point at 2, 2 is an did you say unstable saddle point? How do we know this? A couple things to notice. The eigenvalues are real and different signs. It's really the difference, they're integers and they're different signs. It doesn't really matter that they're integers, it matters that they're not complex numbers. They're real numbers and they have these different signs. So here we'd say since one is negative, one is positive. So that's sort of the comment that we can make here. So really not necessarily caring if these are integers or not. It's worthwhile to point out that they are integers, but really the fact that they're not complex numbers means, okay, real numbers, they have different signs, one negative, one positive, and that's what's important here for us to discuss. So okay, so if we want to sort of explore this a bit further, we'd want to sort of think about general forms. General form for x at t and y at t is we're going to have some constant c sub 1 times e to the minus t plus some constant c sub 2 times e to the t. And we would say that as t goes to infinity, this means that x and y are going to diverge, right, headed to infinity. And this is that interesting sort of effect where we might appear like we're headed towards the critical point at 2, 2, only at the last second to sort of dart away. And we'll come back to this example in a bit, but let's see while it's still fresh on our minds if this is what we're noticing in the phase portrait. So here at 2, 2, yeah, so we have this interesting behavior. Trajectories kind of seem like they're headed towards it and go, nah, and just move away, sort of darting away. So that very interesting saddle point behavior that we've come to really appreciate. Let's talk a little bit more, because I mentioned that it isn't just the Jacobian that we have to look at in order to justify what we're seeing here. There's actually, since we're talking about just these constants being the issue, there's actually a way that we can recenter our system into a new linear system that has 0, 0 as the critical point to justify this a bit differently. And the substitutions are that we would let u be equal to x minus x sub 0, and let v be equal to y minus y sub 0. Now I already went through and found the critical point. The critical point was 2, 2. So it's x sub 0 is 2, and y sub 0 is this other 2 here. So that means the substitutions that we're going to use are let u be equal to x minus 2, and to let v be equal to y minus 2. Now, a couple of things that I can mention right away from these substitutions is, first of all, if I go here and differentiate both sides, we're going to notice that u prime is equal to x prime, and similarly here, v prime is equal to y prime. And that's going to be very useful, because now that means with my substitution, I can also exchange the derivatives very freely. And another good thing to do would be to solve for x and y. So if u is equal to x minus 2, well, that means x is equal to u plus 2. And if v is equal to y minus 2, that means y is equal to v plus 2. Now let me go back to that initial system that we had. So here we had x prime equals 2x minus y minus 2. We had y prime equals 3x minus 2y minus 2. Now I want to start making my substitutions. We said x prime is equal to u prime, so I substitute there. U prime equals 2 times x, but x is u plus 2, minus y, but y is v plus 2, and then minus 2. Get a little border there. And then y prime, we said, well, y prime is equal to v prime, and this is equal to 3 times x, but x is u plus 2, minus 2 times y, but y can be replaced with v plus 2 minus 2. And this should just reshift in a way that now I have a new linear system to look at that's going to exhibit the same exact behavior as this old linear system, just a reshifting of it that now has critical point at 0, 0, and looks like our previous examples. So if I go through this, I get u prime equals, distributing, I get 2u plus 4, bring that minus sign in, we get minus v minus 2 minus 2. So u prime equals, and here I can say, okay, notice with my constants here, 4 minus 2 minus 2 is going to cancel. So I'm just left with 2u minus v. And here with v prime, if I distribute the 3 in, I get 3u plus 6. Bring the negative 2 in, we get minus 2v minus 4, and then minus 2. And with those constants, we have 6 minus 4 minus 2 is going to cancel, so I'm really just left with 3u minus 2v. Now this looks like the systems that we saw earlier. And so it stands to reason then that thinking about u prime first and v prime second, this would just have a coefficient matrix 2, negative 1 for the top row, 3, negative 2 for the bottom row. But that's exactly what we got anyways. So it's just sort of an interesting way to sort of rethink this. Certainly the Jacobian comes in to state this result as well, but I think it's nice to think about this just as a substitution that allows us to now reshift, because now if I set u prime and v prime equal to 0, this now shows that the critical point is at 0, 0. And I don't want to think, okay, so the critical point's at 0, 0 now. That's really not the idea. The critical point for the system that I was given was always at 2, 2. And we solved for that. But this is just another way to justify ignoring those constants, that I can do the following. I can use these pivotal substitutions here to allow me to recenter the system that I was given into a new linear system on u and v, and u prime and v prime, where this is now a linear system without that constant trailing, with a critical point at 0, 0. I can identify the behavior of this new critical point at 0, 0, and that behavior is exactly the same as the critical point that I had at 2, 2 of the original linear system. So this is just a way that we would go through to determine the behavior. So we would say the behavior is the same as our critical point was at 2, 2. Okay. Well, we took a look at this example. We had that saddle point at 2, 2. We saw that earlier. Let's take a look at another example, and same idea. So what we're going to do first is we're going to find the critical point. So we have system x prime equals x minus y, and y prime equals 5x minus 3y minus 2. And if I set these derivatives equal to 0, 0 equals x minus y, and 0 equals 5x minus 3y minus 2, I can work with a substitution again. And this is a great equation to work with, since I can just move y over and say, well, that means y is equal to x. So I can substitute in this other equation here. So 0 is equal to 5x minus 3x minus 2. I can combine like terms. So 0 equals 2x minus 2. If I add the 2 over, that means 2 is equal to 2x. And then dividing by 2, x is equal to 1. Now since I know x, I can find y, and y is equal to x. So that means y is 1. Which means that my critical point is x is 1, y is 1. 1, 1. 1, 1. Now when going to work with the coefficient matrix, it's literally just that, the coefficient matrix. We use the coefficients. This extra -2 as a trailing constant doesn't really matter. And you could go through either of those methods we talked about before. The jacobian, that's a pretty strong tool to use for a linear system that just needs to be recentered, or you could use those substitutions to justify it. But at the end of the day, that's all that we're going to wind up doing, is using those coefficients to build our coefficient matrix. We call it the coefficient matrix for that reason, because it uses the coefficients on x and y. So for that top row, the coefficients on x prime, it's a 1x minus 1y. So 1x minus 1y, we write the 1 and the -1. Second row is going to come from y prime, and the coefficients. I don't even look at this -2. Well, I look at it. I don't want to be rude, but I kind of like say hi to it, but I don't ever really talk to it at the party, right? We got the rest of this stuff is what we're interested in. 5x minus 3y. So 5x, so write the 5, minus 3y. We got our coefficient matrix. So really not too dissimilar, not too difficult compared to what we did at the very beginning. Let's get those eigenvalues. I'm sick of talking about eigenvalues. Everyone says you're all talk. I'm like, no, I'm all action. I want to find the eigenvalues. I'm not just going to talk about finding the eigenvalues. I'm going to find it. We're going to find it. We're in this together. Of course we are. Determinant of a minus lambda I. Let's race. I want to see, can you find these faster than I can? Probably 1 minus lambda, -3 minus lambda. Oh my gosh, what's that? I'm just kidding. I'm trying to fake you out. I don't want you to, we're in a race. I'm trying to trip you up. What is that? Go on to your iTunes real quick. I'm just kidding again. I'm trying to trick you. Negative lambda times negative lambda gives me positive lambda squared. Negative lambda times -3 gives me plus 3 lambda. 1 times minus lambda, that's minus lambda. 1 times -3, that's -3. Minus a negative is plus. 1 times 5 is 5. Equals 0. Combine those like terms. I feel like you're already done. I feel like I'm losing the race. Lambda squared plus 2 lambda plus 2 equals 0. You know, it's not about who wins or loses. I think we're all winning because we're learning. This doesn't look like it's going to factor, not to me anyways. Let's take a look at the quadratic formula. Oh yeah. Oh yeah, lambda is equal to b is 2, negative b is negative 2, plus or minus the square root of b squared, 2 squared is 4, minus 4 times a times c, so that's 4 times a is 1, c is 2, all divided by 2 times a, so all divided by 2 times 1. What do we get here? So this is negative 2 plus or minus the square root of, we have 4 minus 8, all over 2. So lambda is negative 2 plus or minus square root of negative 4, all divided by 2. Use that product property of the radical. So we'll say negative 2 plus or minus, here square root of 4 is 2, square root of negative 1 is I, so we should get 2I all over 2, and now we can reduce. So lambda equals negative 2 divided by 2, that's negative 1, plus or minus 2I divided by 2 is I. And there we have our eigenvalues, negative 1 plus I, negative 1 minus I. What are we thinking about that critical point? That was the critical point at 1, 1 that we found. We have our eigenvalues now. So we'd say since the eigenvalues are complex with a negative real part, what does this mean? This means we have a asymptotically, and we have an asymptotically stable spiral point at 1, 1. So since our eigenvalues are complex with a negative real part, we're stable. That means we have an asymptotically stable spiral point. If you want to think about using some of those other key terms, we could say it's a spiral sink, I think is cool to sort of say. If you're kind of hip with that lingo, then yeah. And remember that this really comes from how these general forms look. Don't be afraid to bring everything back in context to that characteristic equation, right? So we'd say the general form for x and y is we're going to have e to the minus t times c sub 1 cosine t plus c sub 2 sine t. And keep in mind what happens as t goes on to infinity. Well, cosine and sine keeps oscillating. It does its sinusoidal thing. But this exponential function is going to decay it down to 0, which is where we get this really nice spiral effect. But then it's going to end up bringing it right in there into our critical point. And here our critical point is at 1, 1. So that's important to sort of keep in mind here. So here we would say as t heads to infinity, we approach the critical point at 1, 1. So we're saying asymptotically stable spiral point or a spiral sink at 1, 1. Let's see. Face portrait, where are you? So here we're centered 1, 1 for x and y. We got that spiral and our arrows are pointing in. So we are asymptotically stable spiral point. Looks great. I love that spiral effect. We got one more example to take a look at. I think it's not a bad idea to pause the lecture video, try this one on your own, and then resume the video, you know, put it on like twice speed, run through it as fast as you can with me in the video, and just see if you get it right. But I think it's good to sort of practice. So take a look at this one. Let's find that critical point first. So our system, x prime equals x minus 5y minus 5. Y prime equals x minus y minus 3. If I set my derivatives equal to 0, so 0 equals x minus 5y minus 5, and 0 equals x minus y minus 3. Here I could go to the first equation. I could solve for x pretty quickly. Just add 5y, add 5 over. So x is equal to 5y plus 5. This is a great substitution. Plug that in for x into the other equation. So 0 equals, we have 5y plus 5, and then minus y minus 3. We'd like to combine those like terms. So here 0 equals 5y minus y is 4y. 5 minus 3 gives me plus 2. I can subtract 2 to the other side. So we'd say negative 2 equals 4y. If I divide by 4, I get y equals negative 2 divided by 4. That's really negative 1/2. Now that I know y, I can plug in to solve for x. So x is equal to 5 times negative 1/2, and then plus 5. Or here, this is negative 5 over 2 plus 5. 5, if I get a common denominator, is 10 over 2. So then x is equal to 5/2. So here we have our critical point. So critical point is x is 5/2, y is negative 1/2. But now remember, even though we have this sort of critical point that's not at 0, 0, we could still go through either the process of working with the Jacobian or recentering this into a similar linear system now with a critical point at 0, 0, and look at that coefficient matrix. With all of that in mind, we simply don't. We just take a look at the coefficient matrix of what we have already. That's going to give us the eigenvalues and tell us the behavior. So here we go ahead and build that coefficient matrix A. And these should be relatively fast problems because the eigenvalues tell us everything. Let's go to x prime first. So we have 1x minus 5y. We sort of ignore that constant. We needed that information to find the critical point, but not to determine the nature. So 1x minus 5y, 1 minus 5, that's my top row. What about y prime? That's 1x minus 1y minus 3. We ignore the minus 3. Taking the coefficients for the coefficient matrix, 1x minus 1y, so 1 minus 1. And then we build a minus lambda I. So subtracting lambda on the main diagonal, keeping those other entries the same, we can now find the determinant of a minus lambda I, which is going to be 1 minus lambda times negative 1 minus lambda minus negative 5 times 1. Set that determinant equal to 0. Distribute out. So here if we FOIL, negative lambda times negative lambda gives us positive lambda squared. Negative lambda times negative 1 gives us plus lambda. 1 times negative lambda gives us negative lambda. 1 times negative 1 gives us negative 1. And then minus a negative is plus. 5 times 1 is 5 equals 0. What happens next? Well, lambda squared, of course. Lambda minus lambda cancels. Negative 1 plus 5 gives us plus 4 equals 0. And then now if I go to solve, let's say if I subtract 4 over, I get lambda squared equals negative 4. So then lambda is plus or minus the square root of negative 4. And keep in mind from here we would use the product property of the radical. So we'd say, okay, that's plus or minus square root of 4 times negative 1, or that's plus or minus square root of 4 times square root of negative 1. But if you're comfortable with these already, you're probably saying, okay, that's plus or minus 2 times imaginary number I. So we got our eigenvalues, but what are we thinking about for classifying this? So what did you get for the classification of this critical point? And here, as a reminder, critical point was 5/2, negative 1/2. So what do we get for the behavior is a stable center. And how can we tell? The eigenvalues are pure imaginary with real part equal to 0. And that's sort of important to mention here, that since that real part is equal to 0, if I were to try to write general forms for x and y, for x at t and y at t, since the real part is missing, if you want to write it in, that's really a 0 plus or minus 2i. We would say, well, this is going to look like e to the 0t times, in parentheses, c sub 1 cosine 2t plus c sub 2 sine 2t. But that e to the 0t is just e to the 0, which is 1. So in general, this is just going to look like c sub 1 cosine 2t plus c sub 2 sine 2t. So this is just going to oscillate. Because I don't have that exponential function, I have nothing to move my trajectories towards nor away from the critical point. We just sort of end up, pacing around that critical point. So that's what we mean when we say we have that stable center. So stable center at 5/2, -1/2. Let's see what the phase portrait has to say. So notice here the x value is at 5/2 or 2.5, y is at -1/2. So just I've set up this plot so that you can see the critical point right at the center, but I have set these up sort of specially in the axes to do this. What do we have? We have that stable center. Just everything is sort of these rings around that critical point. So we can definitely take a look at the phase portrait to get an idea as to how these look visually to confirm what we said. That's it for the section. Let me go ahead and put the homework in the homework jar. Please take a look at our online homework on our online platform. Let me know if you have any questions on this. It's nice that we can get all of this qualitative information for a linear system just by very quickly finding the eigenvalues. But keep in mind all of those connecting fibers, that those eigenvalues, we talked about this back with our eigenvalue eigenvector method, those help build the general form of our solution. And we're really making a commentary based on the characteristic equation all the way back from solving these differential equations much earlier in the course. So we're building off of a lot of topics. And as long as we're sort of comfortable with all of that foundation, this allows us a very quick response. What is the nature of the critical point? Let me get the eigenvalues. Let me judge them from there. And I should very quickly be able to tell you what's happening at the critical point without even necessarily building the solution in full. But there's always that nice connection that we can make later on. As always, I hope you enjoyed the content. Thank you for sticking with me. Thank you for watching the video all the way through. It's a lot of fun lecturing on this material. I really enjoy this material quite a bit. Let me know if you have any questions on our course discussion board. Let me know if you have any issues with the homework, anything like that. But otherwise, make sure that you keep learning, keep dreaming, and always follow your heart. And I'll see you next time.